morning, everyone, and thanks for coming to our session, Fast Pitch on Carbon. I'd like to, on behalf of my three colleagues here at ARPA-E, thank you for your attention and interest. And I have a few quick comments, opening comments. You know, this issue around carbon is an important one. I think you've all seen the slides that indicate that we're working off of a deficit spending, so to speak, where we've blown our carbon budget over the past couple of centuries. And now if we follow on business as usual, we could be on an irrecoverable path. What it means is that we need to look at both decarbonizing the economy, but eventually get to net zero emissions. I don't know if it's possible to get the slides to, are they up? Okay, on the screen. What we're going to be hearing today is 4 talks that address this carbon problem, looking at some potentially innovative routes to address not just CO2, but also other greenhouse gas emissions. And so the plan is to have each of us speak for 7 minutes. Ian's going to be giving you some really novel ideas about how nuclear can fit in the carbon removal scheme. And Marina is going to be talking about how buildings don't have to just be passive structures, but can take an active role. I'll talk about a different way of looking at our energy delivery systems to see if there's some options that we may not be considering around low-cost, low-carbon energy delivery. And Elizabeth will finish us off talking about how we can essentially reverse what we've been doing for the past 200 years and put the carbon back where it belongs. So with that, I'm going to turn the floor over to Ian. Thanks for your attention. And one last comment, on the back of your cards, there's a QR code. If you could scan that to enter in questions for the sessions, that would be great. Thanks. Ian, the floor is yours.
All right, thank you. Oh, thanks. Thanks, Jack. So today I'm going to be talking to you about how I think that nuclear energy fits into the carbon removal space, and specifically I'm going to be talking about using nuclear energy to operate direct air capture. So at a first glance, I would think that most people would recognize that these are 2 very expensive processes. Nuclear energy is one of the more expensive energy generating processes, and direct air capture is one of the more expensive carbon removal technologies that is also energy intense. So I think, you know, people would first glance say, why is this innovative in the first place? So if you go ahead and you look at, you know, what a potential, you know, process flow diagram would look like, you would get nuclear heat from a nuclear reaction, you would make electricity, and then you would do a thermally driven direct air capture process. Well, I don't actually think that this is the innovative part of using nuclear energy to do direct air capture. So what I actually think is you eliminate the inefficient step of going from heat to electricity to drive a nuclear direct air capture process. Nuclear reactions produce heat. They do not produce electricity, and I think that the mindset needs to be broken that nuclear is only an electricity generating source, but rather a great source of low cost, low carbon energy. So I'm going to talk about, okay, so from the nuclear operator perspective, why I believe that nuclear operators should honestly just ignore electricity generation and go after this limitless need for carbon removal, because it's a very, you know, necessary and energy intensive process that we're going to be doing for the next 100 years. So I would say that, you know, if you're a nuclear operator and you generate 3 megawatt hours of thermal energy, you know, that because of Carnot inefficiencies, you're going to get 1 megawatt hour of electrical energy out, and you might be able to sell that for $20 to $40 on a wholesale market for electricity pricing. You're competing with renewables, but in reality, what you want to be doing is using those 3 megawatt hours of thermal energy to drive direct air capture. And now with a pretty, you know, well-known carbon price, if we can come to consensus that that's about $100 per ton, this carbon is going to be a much better revenue generator than electricity, because you can do 1 to 3 tons of carbon dioxide priced at maybe $100 to $300 a ton, depending on your direct air capture technology. So the real key thing that needs to be developed here is that direct air capture technology that better pairs with a nuclear system. So walking through, you know, a sensitivity analysis that I did, if we look at, you know, the gains that need to be made on the direct air capture technology, and if we can use pretty conservative estimates and minor updates to, you know, a proposed nuclear concept and just use the heat from the reactor, you know, the direct air capture innovation systems are required, and that's definitely something that needs to be done if we were to do a potential FOA in this area. And you know, if we just take conservative estimates for the nuclear energy that would be otherwise used to make electricity, you know, this could result in a pathway that is less than $100 a ton, because we are going past that inefficient step of going from heat to electricity and potentially back to heat. And, well, this is why I believe that you should use nuclear for things that are heat driven. I don't think that you should use it for things that are electrically driven. There are many processes in a decarbonized world that require heat. So, nuclear is the optimal, low cost, low carbon heat source. And why I say that is, well, if you're going to use, you know, cheap fossil fuels to drive a direct air capture process, there is extra CO2 that is associated that you have to capture. So if we go ahead and we assume that, well, we need to capture all of the CO2 if we were to use coal or natural gas to do direct air capture, and you know that is going to come with an added cost, because you're going to generate half a ton of CO2 of fossil carbon dioxide for every direct air capture ton that you capture, and that's going to result in an increased system cost, because you have to have all of that extra capacity for direct air capture plus that fossil carbon dioxide. With a nuclear source, you don't have to, you know, carry, you know, 500 kilotons of, you know, fossil carbon carrying capacity on a 1 megaton a year direct air capture plant, so everything can be more compact, the balance of plant components can be smaller, and you can get rid of the unnecessary balance of plant components associated with using fossil carbon dioxide. And what I think that we really need to go after are these, you know, direct air capture desorption loops that may better pair with advanced nuclear. And what I mean by that is, you know, going after a absorption-desorption system that can operate in a 500 to 700 degrees C range, so you can use some of these, you know, more advanced reactors and potentially deliver low-cost, low-carbon heat to drive direct air capture in a compact system that is land efficient and carbon efficient. So, if we were able to do this, I would definitely welcome any feedback on this idea, and I will be at coffee at ARPA-E tomorrow to, you know, further discuss any integration with nuclear heat, not even for direct air capture, but, you know, just using nuclear heat to drive a lot of these hard to decarbonize industries. Thank you. And now I'm going to hand it over to Marina to talk about HVAC and direct air capture.
Great. Thank you, Ian. All right, good morning, everyone. So I'd like to continue on the theme of direct air capture, and I'd like for us to start by taking a look at the Amazon, the world's largest rainforest and our best known carbon sink. Now, the trees and surrounding biomass that comprise the Amazon and other forested areas around the world serve as a natural air conditioner for our planet by releasing oxygen into the atmosphere and absorbing CO2, thus keeping us cool. And when we move indoors, we rely on mechanical systems in the form of HVAC equipment to perform similar functions to ventilate and condition the space. In commercial buildings, the most common HVAC systems are these, where the HVAC is a packaged unit that is installed on the rooftop of the building. And so, as Jack mentioned earlier, we're going to need somewhere between 5 and 20 gigatons of CO2 removal capacity per year by 2100 to maintain acceptable outdoor temperatures. And so that's really going to rely on a full suite of approaches. And with that motivation in mind, ARPA-E launched the Hestia program late last year, which is really aimed at tackling embodied emissions in buildings by storing enough carbon in the finished building product that you can actually have, hopefully, a building that is net carbon negative over its lifetime. Now, the relative CO2 capacity of an approach like this, as represented by the size of the bubbles, may be smaller relative to nature-based or engineered solutions, but it does offer us a few benefits. First is the fact that we have dual functionality in the form of a finished product that can be used elsewhere. But it also really makes us start to think about how we can find new strategies and approaches to tackling emissions reductions for the built environment itself. And so with that kind of broader vision in mind, I like for us to consider what might be possible in terms of expanding direct air capture mechanisms, and doing so in a way where we can tackle the operational emissions associated with buildings, and specifically around our HVAC operations. Companies like Noya and Solterra Power are already demonstrating what's possible in terms of retrofit opportunities with HVAC systems, and are doing so in order to reduce the upfront capital costs and installation time associated with direct air capture. Now, Solterra Power, for example, reports the capability of absorbing 300 kilograms of CO2 per day in an average building, which on an annual basis would translate to roughly 120 tons. So if we think about the fact that we have 5.9 million commercial buildings in the United States, with widespread adoption, this could provide the opportunity for hundreds of megatons of CO2 removal per year. And this gives us a good starting point to start to consider, well, what if we not only optimize for the operations, what if we not only optimize in terms of being able to remove as much CO2 both in the indoor and outdoor air as possible? What if we also optimize for the HVAC operations themselves? So with that in mind, we have to first really think about the integration requirements and the overall energy balance to be able to integrate these two mechanisms. And first comes the temperature itself. So in the schematic here, this is an example of a solid sorbent for direct air capture, which relies on steam as an input during the desorption stage with CO2 and water coming out. And so the temperatures associated with the HVAC operations need to align with what's necessary for direct air capture. But also the pressures needed for the direct air capture itself need to be such that they don't disrupt the overall airflow and operations of the building. And finally, any sorbent or membrane chemistry needs to be selective and stable for absorbing CO2 while also being suitable for the indoor environment and considering the fact that these buildings are occupied. Now we can calculate the overall CO2 capacity by looking at the air changes per hour. And this is calculated by the ventilation rate in cubic feet per minute, along with the overall volume of the building. The ventilation rates themselves are dictated by ASHRAE guidelines to maintain a suitable indoor environment. And so in the absence of expensive CO2 or occupancy monitoring equipment, the default is to overventilate, which comes with an energy penalty in terms of the HVAC operations. And while that gives us kind of a benefit in terms of maximizing the amount of CO2 we can remove from both the indoor and outdoor air through more and more fresh air exchanges, it does come with the potential deficit in terms of the outdoor temperature and humidity and the impact that has on the HVAC operations themselves. And so I'd like for us to kind of look at HVAC itself really quickly, and specifically humidity. Now, humidity is really on the rise, and the need for dehumidification with air conditioning. As a result of global warming, we have an increased reliance on dehumidification, so much so that humidity loads now are larger than temperature loads when it comes to HVAC emissions, and they continue to grow. And so the interest really of late has been in pushing past traditional vapor compression technologies, which as shown in the red here, are limited by the Carnot limit, and creating new separation approaches that, as shown in the purple, can provide an order of magnitude improvement in the moisture removal efficiency and get much closer to the minimum separation energy. And this also gives the benefit in terms of improving the cooling efficiency as well by separating out the dehumidification and temperature control of the building. But what if we actually use the direct air capture and redesign those materials and chemistries such that we can run dehumidification through the DAX system? This could potentially provide yet another pathway for dehumidification beyond vapor compression. Now, if something like this were to work, that's only the start, because there are a lot of market considerations that have to come into play. And first and foremost is, what does the market itself look like? How do you actually differentiate between the incentives for carbon removal with the incentives for energy efficiency improvements and savings on one's utility bill? So that's really still an open question if this were to work. But also, if we are absorbing that much CO2 in large commercial buildings across the US, what do we do with that CO2 afterwards? So how is that, what form is it stored in? And then finally, how is it transported? What does that infrastructure look like? And that, this could take the form of, solid form or gas form, liquid form, but then we really have to have an appropriate network to do that. And so with that, I'd really be interested in other people's thoughts on how we could co-design HVAC operations with direct air capture and meet both our building efficiency goals as well as our climate goals. And with that, I would like to hand it off to Jack, who's going to tell us about the wonders of dimethyl ether.
Thanks. Well, thanks, everyone. My starting point is a comment that Jenny Kirby made yesterday in introductory comments. One of the roles of ARPA-E is to create new options, ideally disruptive options. And so I'd like to share one that maybe challenges some conventional thinking, and hopefully you'll consider might be a little bit disruptive too. So the notion is that we have 3 energy delivery systems in the US, 3 grids: electric, gas, and petroleum. And if we do this right, we can get the maximum benefit from those existing grids, and we can also get the maximum benefit from the existing infrastructure. And that combination allows us to get the lowest cost, low carbon future. And that's what we're going to talk about. But the key here is dimethyl ether, because this is the tie that binds the grids together. DME is very similar to something you already know, propane. You probably use it in your backyard for grilling. The difference is that central carbon in propane is replaced with oxygen. So just like propane, DME is a gas in ambient conditions, but under slight pressure, it can be moved and stored as a liquid. The advantage of DME compared to some of the other energy carriers that we're thinking about are twofold. First of all, it has significantly higher energy density. It has 6 times the energy density of hydrogen and 60% more energy density than methane. That means if you're looking at a natural gas distribution system, that gas distribution system automatically has 60% more capacity than it has with natural gas. In the case of hydrogen, if you want to replace natural gas with hydrogen, you have to go out and build 2 entirely new gas grids at a cost of trillions of dollars. The other thing is, when you condense it into a liquid by putting it under mild pressure, it has order of magnitude higher energy density. The second thing, and this is equally important, is that it turns out that we all know methane is a bad greenhouse gas, but hydrogen is not necessarily benign. It has a very high short life greenhouse gas warming potential. In contrast, DME has 5 days lifetime in the atmosphere and essentially no greenhouse gas warming potential. So DME looks like it could be an interesting candidate, but what really seals the deal for DME is that it is an extremely versatile fuel. It can replace propane and natural gas for heating. In China, they already use it as a propane substitute. It can replace diesel as a drop-in fuel. It can replace petrochemical feedstocks, and it can power the 1,000 or so peaker units that we have for the electric grid. It's also a gasoline precursor, and in fact, 40 years ago, people were making gasoline from DME in New Zealand in a commercial plant. So this molecule can address 40% of our primary energy needs. So the question now is, well, how do you get this DME? Where does it come from? And it turns out that all of the low carbon paths that we're seeking for green electricity, for green hydrogen, or any color hydrogen for that matter, renewable methane, all of those paths can be used to make dimethyl ether with known conventional technology, nothing to invent. So now we get to the question, this may be an interesting molecule, but of course, what's it going to cost? So here's my one equation. This is your cost of energy. And if you look at your utility bill today, you pay for the cost of producing that energy, whether it's electrons or natural gas, and you pay for the delivery cost. And if you look closely, that delivery cost is more than half of your bill. And that's key for the low carbon future. You also have to buy the end-use hardware. You might have a car, you might have a boiler, you might have a water heater, and you might have to replace those under certain energy futures. So let's talk about this, but let's focus on delivery first. So we have 3 grids, right? The electric grid is the smallest grid. It has a summer and a winter peak. The natural gas grid is about twice the size of the electric grid in terms of the energy delivery. But what's interesting is it's only used rarely. It's not reused at all in the summer. It has a winter peak. And for 3/4 of the year, it's basically underutilized. It delivers about 400 terawatts of energy equivalent. Gasoline is a constant demand, also at about 400 terawatts. If you want to use the electric grid to replace heat, you have to handle that coincident winter load. You have to build 2 new electric grids to do that. If you want to then take on gasoline, you need 2 more electric grids. So let's talk about these grids and what the implications are. The grids all look similar, but there's some big differences. The electric grid costs 4 times as much to build, 4 times as much to build for the same equivalent energy delivery as pipes. It's also the most vulnerable grid to natural disasters, and it's really hard to store electrons. If you look at the petroleum grid, it stores 7 ecajoules of energy at a cost that's 200 times lower. And guess what? You don't need any nickel, you don't need anything fancy. It's called a tank, no technology. If you look at the gas grid, it has this enormous latent capacity, and you get a 60% stretch on that if you use DME. So, what's your bottom line look like in an energy future? Well, here's the thing that's kind of surprising. It almost doesn't matter what the cost to make the green fuel is. It's overwhelmed by the cost to deliver that fuel to you, the price you're going to pay on your monthly bill, and it's also significantly influenced by how much stuff you need to replace. So for example, if we're going to electrify heat, we've got to replace 75 million furnaces, and we may have to replace 270 million vehicles. If you're going to use hydrogen, you need to build out 6 times the gas grid to handle the load. That's a huge investment. And oh, by the way, you also have to replace your appliances. What's interesting with dimethyl ether is it costs a little bit more to make, but you don't have to spend a fortune to deliver it if you use the existing hardware, and you don't have to replace what you've already got. So here's some final thoughts to keep in mind. First of all, DME is just one of many possible energy carriers. Clearly, we're going to need silver buckshot. There will be a role for green electrons. There will be a role for hydrogen. But what I submit to you is to think about other energy carriers that can leverage existing infrastructure and still be green. The markets will sort all this out. Let's not pick winners too early. Let's keep our options open, and that's what ARPA-E does. We create options. The other thing is, I think the lesson here is we really need a system-level analysis. We have to look across the entire supply chain, production, distribution, and end use, because these all have strong cost implications. And what I will postulate is that repurposing existing infrastructure is also green. The stuff that you don't have to throw away and rebuild is also an environmental benefit. So with that, I'd like to conclude. that, DME is certainly an interesting molecule. I hope you'll get to know more about it. This DME can come from renewable sources. It can complement what we're doing, and I think it can help fill the gap in some of our cost objectives. And with that, I'm going to turn the floor over to Elizabeth. And remember to scan the back of your tag for questions for the QR question session, which will be coming up. Thanks.
I'm Elizabeth Troein, and today I'll show you how we can rethink the future of carbon storage and aim for infinitely scalable solutions. So let's dive in and let's see what we can do with carbon. The burning of fossil fuels essentially reverses millions of years of natural biological carbon removal and storage. And since 1850, humans have released about 1,600 gigatons of CO2 into the atmosphere through the burning of fossil fuels alone. And to put this huge number into perspective, the entirety of the built environment has 1,100 gigatons. So the CO2 that we've put into our atmosphere weighs more than all of our roads and buildings globally. And it will take a concerted effort and a lot of energy to selectively remove carbon from our atmosphere to prevent the worst impacts of climate change. And we've heard some creative solutions already in this session on how we can remove this carbon. But I'm here to emphasize that we must scale our storage solutions alongside our removal solutions. We need a place to put all of this carbon. And to give you a sense of the scale of current carbon storage solutions, globally, about 7 million tons of CO2 per year are stored in dedicated subsurface CO2 storage reservoirs underground. And Orca, the largest direct air capture and storage project to date, has a capacity of about 4,000 tons of CO2 per year. So with current storage solutions, we're talking about kilotons per year and megatons per year when we need to get to gigatons per year. So what ultimately is limiting the scalability and how quickly we can scale the existing storage solutions? And of course, this will depend on the pathway, and we'll talk about a few key pathways today. When we look at solid storage of CO2 as carbonates, this is the reaction of cations with CO2 to form solid phase carbonates that can be stored. And this reaction relies on the consumption of cations that must originate in rock. And it can take about 1 million tons of rock for every ton of CO2 that is stored. And this rock needs to be mined, crushed, dissolved, and reacted in order to form these carbonates. So ultimately, mining and reactivity can limit how quickly we can scale these storage solutions. And for solid storage as biochar, this is the processing of biomass into a stable form that can be stored on land. And since this is a biological process, like all biological processes, it is limited by nutrients, nitrogen and phosphorus, at a fixed ratio to carbon. And phosphorus also must ultimately be mined. It must originate in rock. We cannot fix phosphorus from the atmosphere like we can do with nitrogen. And as with all plant-based biological processes, this will also be limited by arable land. So the availability of arable land in a given year can impact the scalability of this carbon storage solution. And we may think about subsurface pore space storage as supercritical CO2. Ultimately, what limits the capacity and how quickly we can scale this storage solution is how quickly we can get CO2 underground. So this not only involves the transport of CO2 from where it is removed from the atmosphere to where it will be stored underground, but it also depends on how quickly we can get that CO2 underground in Class 6 wells. So how quickly can we build out these injection wells? And can we build out a pipeline, or can we cost effectively transport this CO2? And those are open questions that may limit just how quickly we can scale. And it is likely that all of these solutions will be important to carbon storage, especially in the short term. But how can we use the technical, the things that limit the scalability of these solutions from a technical perspective to frame the next generation of carbon storage solutions? Can we reduce or potentially even eliminate any stoichiometric mining requirements? So can we eliminate the need for consumable reactants that must be mined? Can we reduce or even eliminate the need to transport the CO2? To transport, can we make a form of carbon that is either easier to transport, or can we make a form of carbon that we can store anywhere? And can we eliminate the arable land requirements to make sure we're maximizing the potential to scale, especially in a world with a growing population with an increased demand for food? So I'll present a few potential pathways just to get your creative juices flowing. Can we think about alternate minerals? So can we think about potentially going through an oxalate pathway, which can store twice as much carbon per cation compared to carbonates? Or can we think about leveraging the formation of sodium aluminosilicates, which could potentially use a brine-based cation source and would potentially eliminate the need for new mining? And can we think about artificial photosynthesis? So right now, artificial photosynthesis is being implemented to take CO2 and make carbon-based fuels, but biology creates a lot of solid phase biopolymers that contain carbon. Can we optimize the production of these polymers for dedicated solid phase carbon storage? And can we think about how to scale catalytic CO2 to solid carbon? So this method has been implemented in the lab. It does not require, it is regenerative, so it does not require any reactants that are consumable, and could potentially scale as long, and another thing to consider though is, can we make these solutions cost effective and competitive? So as we're thinking about these creative pathways, can we minimize cost and maximize scalability? And ultimately, I want to hear from you. I want to hear all of your creative ideas in this space. How can we achieve infinitely scalable carbon storage? So please reach out. Find me at the coffee at ARPA-E tomorrow morning, or any time. Please reach out, send me an email, and let's see what we can do about carbon. Thank you.
Well, looks like we have some questions coming in here, so hold on a second. This works a lot better if I put these on. First question for Ian. Why is nuclear the cheapest form of heat? Why not use solar heat, geothermal, or PV cheap renewables to heat?
Yeah, that's a good question. So when you kind of look at the numbers, if you kind of go ahead and you look at the CapEx numbers of solar and solar to thermal, you're limited to the capacity factor. And then when you counter the capacity factor with nuclear, and you kind of do the analysis that shows, well, if you go from nuclear heat at some high grade heat, that it ends up being that nuclear heat is actually the lowest cost solution compared to inefficient steps of going from electricity to thermal, or limited capacity factors. But it's really a question of what temperature do you want to use for a direct air capture process. I know that Climeworks is using geothermal in the Orca plant, I think in Iceland, but I think that you can really drive down the CapEx on that direct air capture side if you have a higher grade heat that is also a very similar low cost.
Okay, Marina, a question for you. What trade-offs do you envision exist between maintaining occupant comfort and maintaining optimal DAC operation?
I couldn't hear that.
What are the trade-offs between comfort and DAC?
Yeah, it's a good question, right? Because we've definitely seen during the pandemic an increasing reliance on the traditional over-ventilation, so bringing more and more fresh air in, and that it has an energy penalty to it. While it does remove a lot of those pollutants, it can also bring in a lot of humidity, and you have to deal with kind of the temperature gradients. I think ultimately it's going to really depend on what type of DAC approach one takes, and what the requirements are going to be associated, in particular with the pressure, to make sure you're not disrupting the airflow requirements. So there's definitely these trade-offs that need to be balanced out. between, what's the optimal in terms of the overall CO2 removal, in particular exterior outdoor air CO2 removal, and that interior climate. But if we could actually use that DAC approach to run the dehumidification strategy, that really, could unlock new opportunities in terms of what those trade-offs look like.
Thanks. I'm going to try and answer two questions at once. One was about how does DME compare to methanol, and then what is the carbon intensity of DME? The short answer is you make DME by first making methanol, and then you do what's called a condensation reaction and turn two methanols into one DME, and you reject water. So you actually go through methanol to make DME. The second question is the carbon intensity, and the carbon intensity depends on the path. So Oberon, for example, out in California, is looking at using biogas from dairy farms. They can actually get a negative carbon intensity for their dimethyl ether, but it really is a path-dependent process, depending whether you start with green electrons, what color hydrogen you might start with, and how you're going to get the carbon source. So all I can say is it depends. Hopefully that's a satisfactory answer for now. Elizabeth, question for you. For new opportunities to store carbon, what innovations technology needs to take place to concentrate the CO2?
The question was what innovations need to take place for concentrating the CO2? Read that one more time.
Yeah, what new opportunities to store carbon and what innovations technology need to take place to concentrate the CO2?
Yes, great question. So yes, I'll start by saying as we think about storage solutions, we can think about storage solutions that either take advantage of the CO2 stream coming off of direct air capture processes, for instance, but we could also think about ways, so any of these like enhanced weathering or geomineralization processes that maybe we could extend to like an oxalate system that could potentially take CO2 directly from bulk air. So we may not need to go through a CO2 stream, would maybe be my first answer to that question. But another thing we need to think about is thinking at like a systems level. So ultimately, will the cost of electricity ultimately limit a given pathway, or will a given reactant, if we are looking sort of at a pathway through which we're minimizing reactants rather than eliminating them. Basically, I think we should think a little bit holistically about how we ultimately store our carbon.
Thanks.
Yeah.
I guess I'll field the next question to me. Can you blend DME in gas pipelines, or do you need to convert the pipelines to 100% DME? So it's an interesting question. The utilities a number of years ago, before the shale gale, were looking at importing LNG, and DME was one of the agents that they were considering in at both the transmission and the distribution level to adjust for the heating value of the gas. The DME is similar to propane. So, for example, the gas utility that I work for, we used to use combinations of propane and air to peak shave our gas utility in periods of high demand. So the short answer is you can blend it in. You do have to watch for what's called the Wabi index, and you may have to change the orifice on certain appliances if you get too far out of range, depending on where your blend is. But it is compatible with the gas system. You'll have to change the meter, though, to make sure the meter is measuring the right number of BTUs, just to recalibrate it. Let's see, question from Marina. Do you think you could use the existing natural gas pipes into the homes and businesses to get the CO2 back out again?
Yeah, that's also a good question, and one I've certainly thought about as well. I mean, it could definitely be conceivable. It's not trivial by any stretch of the imagination. The question there would be, would any retrofit kind of be required to handle the CO2? But certainly that might be a potential pathway if those pipelines are no longer being utilized as more and more buildings electrify.
Okay, and Elizabeth, question back to you again. How does the energy required to run the CO2 conversion processes compared to the conventional ones, especially for oxalate and direct CO2 reduction to carbon?
Yes, so the energy requirements would potentially be large, and just really roughly speaking, as we're thinking about removing and converting carbon, it may take as much energy as we received by, say, burning the fossil fuels in the first place. So we are talking about large amounts of energy. So that's why, as we're thinking about future scenarios, the cost of electricity will have like a large impact on which carbon storage solution is ultimately the best one. So yeah, right now I'm looking to see if there are creative solutions for minimizing this energy requirement as much as possible, while also achieving scalability. So it will require definitely a lot of energy. So it's a matter of, can we minimize it for scalability?
And Ian, a question for you. So we have a lot of nuclear plants that are being threatened with shutdown because they can't compete in a $20 electric market. What's stopping us from using those things today to become DAC-centric profit sources?
Well, so there are a couple things there. So one, the technology that you would probably pair with a light water reactor is going to be very different from the direct air capture technologies that I would be proposing to develop. You would probably be using some sort of low temperature solid sorbent or an amine-based approach that desorbs at about 100 to 150 C. These solutions may be potentially expensive to integrate with direct air capture, and on top of that, we still don't have a viable carbon market to sufficiently drive economic incentive for direct air capture. There are definitely some ways of thinking about that. There are voluntary carbon markets, but an uncertainty in developing something with a nuclear plant is probably a big factor in that development process.
Okay, and Marina, another question for you. Sorbents have low capacity and high energy requirements to regenerate. Is using electrochemical carbon separation for building ventilation a possibility?
Yeah, I mean, it's definitely a potential pathway, and I really think that we have to go back to the drawing table and not just use what's already out there in terms of DAC systems, but design something from scratch with the objective of the building operation too. And so that it could certainly potentially be electrochemical. That comes with trade-offs as well. So you have to kind of look at that full system and what comes in and what comes out, and what would ultimately make sense.
So here's a question to me. DME sounds very promising. Why hasn't there been more traction around this far? Is it because of production processes? Well, it's actually quite interesting. There's like there are advocates for every molecule, I suppose. There's actually an international DME coalition. And I think it's partially a couple of things. One, the low carbon benefits haven't been recognized. And two, there's been a lot of interest in other molecules or hydrogen, electrons, et cetera, and it's maybe taken us down, one path. What's interesting is that SHV, a Dutch company, and UGI, a US company, those are the number 1 and 2 largest propane companies in the world. They just won an award from the World Propane Council because they are looking to convert their entire systems over to renewable DME. In China, where they were using a lot of wood and even dung for home heating, they have converted some of their coal to methanol projects to produce DME for domestic heating. So Volvo had a program 20 years ago running diesel trucks on DME with a lubricity agent. It's always hard to say when the time is right for a technology. So again, what I would suggest is get to know this molecule. Maybe there's something there that you'll like, and you may be the next advocate. Elizabeth, question for you. In a system that forms solid carbon products, do you foresee landfilling the product or some additional use?
That's a great question. So yes, I think something that could be really interesting is implementing this solid phase carbon in the built environment. That could be a really great way to store vast amounts of solid phase carbon, so something to definitely consider. But we could also consider landfilling could be an option, just depending on the end uses that we're able to envision. And maybe if we can integrate a solid conversion with upgraded materials, as long as those materials will have a long lifetime, I think that could be a great solution.
Okay, and Ian, a question for you. So nuclear plants are heavily regulated. Would you need to do something special to get them permitted for DAC?
I'm really not sure about I'm not really sure about the regulations if you were to do nuclear integrated with direct air capture, but one of the things that you would be able to do is it kind of removes the geographic limitations of going after power generation markets, in the sense that you want to minimize transmission and distribution lines. You would feasibly be able to put these direct air capture plants anywhere in the country that has a CO2 basin available for you, or a solid carbon product that Elizabeth is talking about. So you might be able to alleviate some of those approval processes, but to date, I don't think that any of the advanced nuclear reactor companies have gotten approval yet, so it remains to be seen.
And maybe a follow-on question that just came in. How would the DAC process itself change if you were to use this new high-grade heat from these advanced nuclear processes?
Well, you would have to really design a system that is going to desorb CO2 between 500 and 700 degrees Celsius. So the two approaches today are low temperature, meaning 1 to 200 degrees C desorption temperature, and there's carbon engineering's process, which is desorbing calcium or CO2 from calcium at about 950 degrees C. High temperature gas reactors might be able to pair with that, but you're really pushing the limits of what a high temperature gas reactor can do. So I think that it's better if you can find a system that can better desorb in that 500 to 700 degrees C range. Maybe a molten salt, but we'll see.
Okay, and Marina, so we're going to reuse buildings to capture carbon. How much of the stuff do we actually get to reuse in the HVAC system?
Sorry,
how much of the hardware do we actually get to reuse from the existing HVAC system?
There's a good kind of starting point in looking at what companies like the ones I mentioned, Noya and Solterra Power are doing, where they're using the air handler system itself. They're really using the ventilation piece of that CapEx as an input for the DAC, and then attaching the DAC kind of system on top. Now, those are retrofit examples where you're taking what you already have. In theory, if you're redesigning a system from scratch, you may have fewer kind of pieces that you need, or kind of a design strategy that leverages those a little more. But really, like the fans and the air handler system is what is used to kind of attach the DAC.
Okay, and a question for me. Elaborate on how you'd actually produce DME in a sustainable way. So the first thing to imagine is just biomass gasification. Biomass gasification, you produce syngas. From syngas, you produce methanol, and then you turn methanol into DME. And that's a very well-known process. And in fact, my former organization, the Gas Technology Institute, worked with Haldor Topsoe to actually not just stop at DME, but to take biomass all the way to gasoline using DME as an intermediate. So that's kind of a biomass route. You can also start with renewable methane, and it's a well-established practice to take methane to methanol and then on to DME. You can also start thinking about some novel approaches. For example, if you make hydrogen green, blue, whatever color, you can react that directly with CO2. That's a conventional methanol reaction, and you can make DME that way. Or you may be able to electrochemically reduce CO2, and ARPA-E had a workshop on this topic a few months ago, and combine that with hydrogen to make methanol directly, and then again make DME. So there's any number of routes. I think the important thing is any of the renewable routes that you can use to make either green electrons, green hydrogen, green methane are also amenable for making green DME. Question for all panelists. What further research is needed to get to commercialization? So we'll start at the end here.
Research to get to commercialization, so that would be the ultimate, definitely commercialization if you're going to get to scalability. So I would say reducing costs would be the first. For any pathway, so I won't choose one, but for any pathway, getting costs down would be the first place I'd start.
Yeah, so in terms of commercialization today, when you look at these systems separately, there are commercial products out there, and so I think really then the first steps in terms of research when really integrating them together is to be able to come up with approaches that really tackle the material science and the chemistry in a way where your overall energy balance looks good and optimizes for indoor comfort primarily, while then kind of maximizing the CO2. But it's really kind of at the heart of that initial engineering design is where I think there's potential for great research opportunities.
So I'll start with the direct air capture side. So I'm a firm believer that there are great systems that do air contacting already. And on the back end, if you want to pair with some of these nuclear heat sources that are in between 500 and 700 degrees Celsius, you have to find a way to desorb a material within that temperature range without minimal updates to the nuclear side. So off with the primary loop, or probably a secondary loop on a nuclear plant. But if you want to make significant advances on the nuclear side, you will need to really push the temperature higher, maybe above 1,000, maybe like 1,500 C. But that's going to require materials engineering for extreme environments. You're talking high temperature, radiation, different environments, I would say, that we don't really have a good handle on today. So there are two ways to do this, but I believe that, if in the near term, it's probably on the direct air capture side, but on the long term, if you really want to drive the temperature of the nuclear process up, it becomes a material science challenge of making materials for extreme environments.
And I guess for my part, in my talk, I talked about, there's a production, and then there's a distribution, and finally the end use of these molecules. On the production side, there's really actually been very little work done on DME. Mobil, they developed and commercialized a natural gas to DME to gasoline process 40 years ago. There hasn't been much work. I mentioned the work at GTI with Halder Topsoe. I think it's really interesting to think about direct electrochemical reduction of CO2. And in fact, Ian was one of the leaders for our workshop looking at the notion of combining carbon capture with carbon reduction to skip the step where you regenerate the sorbents. Instead, you just react the CO2 to something useful. So I think there's a lot that could be done on the production side. When you get to the distribution side, it's really engineering studies, not so much new technologies, but understanding how you're going to handle the blends and what are some of the particulars around the pipeline conversions. On the end use, there's endless opportunities to explore what you could do with this molecule. Volvo ran trucks on it, and Oberon's converting forklifts to it. But I think there's all kinds of opportunities to explore where else it could go. Let's see, I think we have time to maybe go through one more round. Question for all the panelists. If you could see advancements in just one part of what you're proposing, what would it be? And we'll start again at Elizabeth.
Ooh, that's a great question. So I'd be interested in seeing definitely advancements in how to minimize this need for consumable reactants. And I think what I'd be really interested in seeing is can we either use brine-based cations, or can we get 2 for 1 for anything we need to mine? So I find that to be really interesting. Love to talk more.
Yeah, I mean, I would be really interested in the area of non-vapor compression and like new separation approaches is really hot right now in the HVAC space. So I think it would be really cool if we could leverage DAC to come up with more creative solutions and really be able to see those types of solutions actually implemented and deployed, which can be really challenging in the built environment because building owners and operators are rightfully very conservative when it comes to testing out new technologies. But perhaps when we're thinking about these dual incentives, if we structure it the right way, it could really drive them to make those changes.
Yeah, so I know I talked a lot about the direct air capture side already, so I kind of want to hit on a more general theme for nuclear. I think that we really should try and integrate nuclear heat with any industrial process that is thermally driven. So an example of that is, there's a big focus right now to use solid oxide electrolysis cells with nuclear plants, but I'm a firm believer that you should actually be using a thermochemical decomposition technology to drive off and make hydrogen, for example, or do direct air capture or something like that. You want to use nuclear to do what it does best, which is produce heat. And we haven't really done a great job of figuring out how to do that because I think the mindset is still to use electricity first. So yeah.
And I guess for my wish list for Santa Claus would be for someone to do a system level analysis of looking at, as we try and move to a green economy, what are the system level costs, and explore what are the options and the optimal uses of our existing infrastructure, and how do we bring these new energy carriers, whether it's green electrons, hydrogen, DME, ammonia, into play to see what is the lowest cost option at the system level, considering not just the production, but the distribution, and equally important, the changes we have to make in our end-use investments. So with that, I'd like to thank you, the audience. You've done a great job. You've kept us very busy and on our toes and hopefully kept us honest. We're all going to be at coffee for ARPA-E, and as soon as we get rid of our microphones here, we will probably be swarming someplace down around here or out there in the break area. So thanks again. Look forward to catching up with you, and appreciate your interest.